All right, let's talk about this a bit more, and then we'll do some more examples. I realize my shortcuts here, I needed to annotate them a little bit better. So let's look at C and D. One thing I don't think I made clear is in all of these examples, the mole ratio stays the same. You get the mole ratio from the original equation. So this equation tells us that for 4 moles of aluminum, we need 3 moles of oxygen. The mole ratio then is 4 moles of aluminum per 3 moles of oxygen. All right? And you can use that as a conversion factor just like all those other problems, either that way or flipped, depending on whether you're trying to calculate one or the other. So for instance, if you want to know how much O2 you need in, let's say, part C, we say, okay, well, we have 16 moles of aluminum, and we can multiply that by 3 mole O2 over 4 moles of aluminum. That way the moles of aluminum cancel, and you're left with moles of oxygen that you need, which in this case is 12. Then you compare that to how much you actually have, which according to the problem is 13. And since you have less, or since you need less than you have, then aluminum must be the limiting reactant. Now the theoretical yield is the same procedure, but with the limiting between the limiting reactant and the product that you're looking for. So now we go back to the equation and we say, well, this also tells us that there are several conversion factors we can write here. 4 moles of aluminum per 2 moles aluminum oxide. We could also say 3 moles of oxygen per 2 moles of aluminum oxide. That would be the third possible mole ratio that we could use here if we needed to. Since our limiting reactant is aluminum, that means that the theoretical yield, we need to take those 16 moles of aluminum and again use that ratio, and we use a ratio where the moles of aluminum cancel and we're left with moles of alumina or aluminum oxide. So the theoretical yield is the exact same procedure, just using one of the products instead of the reactant. And using the only trick there is you have to make sure to use the limiting reactant, or you're going to come up with too big of a theoretical yield. If you use the one that you have extra of, you're going to end up with too big of the theoretical yield. All right. So this extra problem then is actually the same, but we need one more step. So I'm just going to copy this. We'll use that same mole ratio, but first we need to find the actual number of moles of aluminum and oxygen.
Are we skipping D then?
Do you want to do D?
No, I mean...
I'll leave D as a mystery for you to figure out on your own for now. We can come back to it later. Let's look at this one. All right, anytime you're asked for calculation of some quantity here, you have to get everything in moles. That's always the first step. And you have to make sure that things are stoichiometrically appropriate, meaning that they're in the right ratios. Or if they're not, you have to figure out which one is the limiting reactant. So the first step is always moles. The mass means nothing to us in terms of chemical ratios because different elements, different compounds have different densities. So we take 3.76 grams of aluminum times 30 grams per mole. And what do you come up with here? Divided by 3. Everybody get this? So that's 0.125 moles of aluminum. Oh, yeah, 27, sorry. It's hard to see from this far away. So what is that actually? Yeah, that sounds better. Okay. 0.139 moles aluminum. And then we do the same thing with oxygen. 2 grams of O2. Molecular weight of oxygen is about 32 grams per mole. We get about 0.12. Yeah, 1/16 moles of oxygen. All right. So now we use that same 4/3 mole ratio to figure out which one's limiting. You can start either way. Doesn't matter. I'll start with the aluminum again since that's what we've been doing. So 0.139. Well, okay, let's make this a second step. 2. Look for limiting reagent. So 0.139 moles of aluminum times our same mole ratio from before, 4 moles of aluminum per 3 moles of oxygen. How much oxygen do we need then? Point what? Okay. All right. And how much do we have? 0.0625. So that's considerably less than what we need. If we have less than what we need, then that one must be limiting. Okay. So then we know that this quantity is the limiting quantity. We cannot make more product than what 0.0625 moles of oxygen will make. So then our third step is calculate yield based on limiting reactant. So we've got 0.0625 moles of oxygen times 2 moles of product per 3 moles of oxygen. And that means we can get 0.0416 moles of product. All right. And then we can finally convert that to mass. What's the molecular weight of alumina of Al2O3? What? And so finally we'll get 3.25? Something like that. All right? Yeah, okay. What is it? What should it be? Okay. Okay. Okay, let's try another one. So for the first one, for part A, how many people found that titanium was limiting? And who found that fluorine was limiting? Okay, a little bit of a disagreement there. Let's go through it. Can you tell from just these numbers, 5 grams of each? Can I say you've got 5 grams of each, we need 2 of this, so therefore fluorine must be limiting? No, it doesn't work like that, right? Why doesn't it work like that? Because we need moles. Remember, the mass tells us nothing. We need to get to the moles. So let's do that. 5 grams of titanium is how many moles? 239? 0.104. And 5 grams of fluorine F2 is how many moles? Okay. Now we can get a little bit better picture of this. If we have 0.104 moles of titanium, how many moles of fluorine do we need? 208, because it's 2 to 1, right? So that means what's limiting? The fluorine. We need 0.204, we have 0.132, so that one's limiting. So when we figure out the yield of titanium tetrafluoride, or titanium fluoride, titanium 4 fluoride, which number do we use? The 0.104 or the 0.132 of fluorine? Yeah, the yield has to be based on fluorine because that's the limiting reagent. If this is limiting, then that has to be used to calculate our theoretical yield. And how much? Then what is the theoretical yield of titanium fluoride in moles? Should be the same number, right? The equation tells us it's a 1-to-1 ratio. So that means we should ultimately form the same number of moles. Oh, yeah, sorry. I was looking at the titanium. So it should be half of that, right? Because the ratio here is 2 to 1. So half of that oops. It's 0.066 moles titanium. So that's how much product we would expect to form. And then you could convert that to grams and you get... Wait a second. We get what? That sounds about right. You got 5.66? All right, let's do it. So times, what's the molecular weight of titanium 4 fluoride?
You guys got 124?
So 0.066 times 124?
Yeah, 8.1.
Okay. So that should have been... Okay. We'll work on some more of these during the problem discussion period on Monday after the lab as well. But let's move on a little bit and talk about solution stoichiometry. We'll talk about this for a little bit, take a break, come back, work some more problems, talk about some more fun stuff. All right, so often things dissolve in a medium called a solvent. You know that. We've done that. We'll do it more throughout the semester. It's an important part of chemistry and of our everyday lives. And when that solvent is water, of course, it's an aqueous solution. We've talked about that. We've mentioned it. We've talked about ions being an aqueous solution. But we haven't really specified what exactly happens. All right, so you know some stuff about water. Water is remarkable. There's really nothing like it on Earth. It does things that other compounds don't. It exists in all three of its phases at normal Earth temperatures. That's solid, liquid, and gas, which is very unusual. High heat capacity, which means it can be heated. It can absorb a lot of energy without changing temperature, or without changing temperature quickly. It has a high boiling point for something that is as small as water is, molecular-wise. Remember, the other liquids on the periodic table are things like mercury and bromine, these heavy things. If you think about gasoline and oils, are these compounds with huge molecular weights, and water is so small. Expands not just upon cooling, but upon freezing. That's very unusual. Usually a liquid is less dense, and then you freeze it and it becomes more dense, but water is actually the opposite. Ice is less dense than water, which is why it floats. And of course, it dissolves many different substances. So what can it dissolve? Well, certainly ionic compounds. We've seen those. Sodium chloride, salt, does some of that. Some covalent molecules as well. Sugar, ethanol, right, any of that sort of thing. And then we need to talk about what it means to dissolve something in water. So let's look at the structure of water, and then we can figure this out. The structure of water, and we'll talk about where these structures come from later in the semester, but for now you just have to believe me and your textbook and the rest of the world, that water is a V shape with the oxygen in the middle and the two hydrogens. Okay. Those are covalent bonds. They share the electrons. We've talked a bit about that. You know that. And here's the important part. Is there a strange noise? What is it?
In the wall over there.
All right. Yeah, probably. Nobody breathe for the next hour and a half. Yeah, next 2 hours. Yeah, sorry, I don't know what's going on in there. Anyway, the important part of water, of the shape of water, is that there are differences between the oxygen and the hydrogen in how they attract electrons. So those covalent bonds are not actually equally shared. The covalent bond isn't exactly the same around the whole molecule. It's a polar covalent bond, which means that the electrons spend more time on one side than they do the other. And the side they spend the most time on is the oxygen side. So that leads to this charge gradient. The oxygen is partially negative, and the hydrogen is partially positive. And you see that in the space-filling diagram here. We show a partial charge by using the Greek lowercase letter delta. If it were a full charge, like an ion, we just write the full charge. But it's not actually a full charge. It just means that the oxygen is a little more negative, the hydrogen is a little more positive. And this is why it's so important. This polarity of water, this is what's so important. This polarity of water is what gives water its dissolving power. So what's actually happening when you dissolve something in water is the molecules are deciding that, well, okay, that gives them a little bit of a weird consciousness, but let's say deciding that they would rather interact with water molecules than with themselves, than with others of themselves. Right? So you have a sodium chloride lattice, which is this collection of positive and negative ions. That's the salt solid that we know. When that goes into water, the ions realize that there's a more favorable energy interaction in dissociating, pulling apart, and aligning themselves up with water molecules rather than staying with the salt molecules. And something that's not soluble in water will decide the opposite. So something like oil has stronger interactions among its own oil molecules than with the water molecules, so it doesn't break up and associate with the water molecules. Okay? And you can see specifically how these things interact as well. So the solute, the thing that you're putting in there, dissolves, and these interactions between the positive and negative parts of the solute start to break up as they associate with water molecules. The positive ions will associate with the negative parts of the water, and the negative ions associate with the positive parts of the water. And you form these little solvation spheres where the water molecules surround the ions and separate them from each other and lead to a more stable situation. So that's what solvation is. Because of that, when we talk about moles and reactions and quantities and all of that stuff in solution, it's going to be different than talking about things in the solid state. Because in solution, we can't talk about a molecule of ammonium nitrate, NH4NO3. We have to talk about ammonium atoms and nitrate atoms because they are indeed separate in water. Same thing with magnesium chloride. We don't have a magnesium chloride structure in water. We have magnesium ions and we have chloride ions. And that's going to change a couple things. So, as I mentioned, some molecules don't dissolve in water. The nonpolar bonds, the ones that don't have this charge separation, they can't interact with the water molecules. They can't form those solvation spheres. And so instead they stay together and they don't dissolve. And that's why things that don't dissolve in water don't dissolve in water. You need other solvents. All right. Let's get some definitions down. I know you've heard some of these before. We know about mixtures. A solution is a homogeneous mixture, but I would say it's a little bit of a special one because it's not simply a physical. I think we can be a little bit more nuanced now. We talked about mixtures as being a physical kind of arrangement of molecules, and you think about grinding something until you can't distinguish the parts anymore, and that's a homogeneous mixture. A solution's a little bit different. It's true that it can be separated by physical means like evaporation, but there's definitely a chemical component to the way that a solvent and a solute interact. And so I think a solution, it is a homogeneous mixture, but it's a little bit of a special one. So here are the words we're going to say now. So please try to keep these straight. Solute, the thing that you put in. The solvent, in this case water. We're going to be talking about just aqueous solutions for a while. And then the solution is the mixture. You can determine whether something is very well dissolved or not well dissolved by measuring the electrical conductivity, assuming it's an ionic compound. How is electrical conductivity measured? Anybody ever seen that? Done that? Well, you simply get something that electricity is passing through and stick it in a solution. And if the electricity continues to flow, it's conductive. If it doesn't, it's not. And you can measure the degree of that. And I think we're going to do that in lab. I don't know if it's Monday. I think it might be the next week. We actually have a light bulb that has some separated components, some separated wires. And you stick the two wires in your solution. If the light bulb lights up, it means that the current is continuing to pass. And so the solution must be conductive. So a couple more terms. Strong electrolytes ionize completely. A strong electrolyte means a substance that when you put it in water completely dissociates. There's no original stuff left over. It's just the ions are surrounded by water. You can have a weak electrolyte that partially ionizes. And you'll talk a lot about those next semester if you take the second semester part about how to determine how much is there and so on. And then you have non-electrolytes, things that simply stay with themselves and do not ionize, do not conduct electrical current. I'm sorry, I said stay with themselves. That's wrong. They do indeed dissolve in the water, but they don't conduct electricity because they're not charged. They don't ionize. Here are some examples of that, a picture from your book. You've got sugar on the left, which is a non-electrolyte. Sugar does dissolve in water, but it doesn't ionize. It doesn't form any charges. So you can't, it doesn't conduct, that water with sugar in it doesn't conduct electricity. Weak electrolyte in the middle, acetic acid partially dissolves in water, and so you'll see maybe a dim light coming on with this type of experiment. And then sodium chloride is a very strong electrolyte, completely ionizes, puts lots of ions in the solution, and that will allow all the current to pass through it. Again, some definitions. Strong electrolytes. Soluble salts are mostly strong electrolytes, and we'll talk a little bit about solubility rules in a little while. But when sodium chloride dissolves in water, there are no NaCl units around, pretty much. Only the ions. That's a strong electrolyte. Strong acids are also strong electrolytes. And in fact, this is a common confusion because when you think of strong acid, you think what? What does it mean to you that something is a strong acid? What? Corrosive, really, is what we get it confused with. When we think strong acid, we think eating through our faces, and you put a drop on the floor and it goes 5 floors down and all of that sort of thing, right? But actually, the chemical definition of a strong acid is simply one that dissociates completely in water. Now, those acids listed can be strong, but actually the acids that you hear about as these like dissolve bones and eat through floors and that kind of thing are often technically weak acids, like HF. Hydrofluoric acid is an example of that. It doesn't dissociate completely, but it is extremely corrosive. It can cause a lot of damage. Those are separate quantities. Let's draw some dissociation reactions now. So HCl is put into water. What ions does it form? Yeah. H plus Cl minus. Great. What about nitric acid? And nitrate minus. Okay. What about H2SO4? Yeah, it's actually, this one's a little bit tricky. The strong acid part is losing a hydrogen and forming H plus and bisulfate, HSO4. Of course, then it can lose another hydrogen and form 2H plus and sulfate. But that's actually not a complete dissociation. So HSO4 is a weaker electrolyte. H2SO4 is the really strong one. And then perchloric acid forms H plus and perchlorate. We're going to talk about some different definitions of acids throughout the semester. The first one is the Arrhenius definition, the least general, and it says that a substance that produces H plus ions when it is dissolved in water is an acid. Okay. That's fine, that'll work for us for a while, but we're going to meet some things that don't necessarily fit that definition. Here's an example of where it gets a little bit weird. It's going to actually affect our stoichiometry calculations and our molar calculations, because when things are dissolved in water, we have to figure out how many of the actual ions. Sulfuric acid, for example, which we just talked about, has the capability of forming 2 H plus ions in water. So that means when we talk about a particular concentration of sulfuric acid, we're actually going to have twice that concentration of H plus. And we haven't gotten into concentrations yet, but that'll be something to watch out for in a minute. And, often neglected, but still important, strong bases do the same thing. A strong base is not one that is corrosive or hurts you, although in a lot of cases they are, but in which it is completely dissociated in solution. So if potassium hydroxide dissociates in water, what ions are formed? Sure. K plus hydroxide. And with sodium, very similar. So those are the strong electrolytes. Now let's look at the weak ones. Now when we talk about weak electrolytes, they're actually pretty weak. Only usually about 1% of the molecules that you put in will actually dissociate in water, as opposed to close to 100% of the others, of the stronger electrolytes. And most weak electrolytes that we talk about are weak acids and bases. There are weak electrolytic salts as well. But something like acetic acid when it gets dissolved in water, so let's actually add it to the water here, it does form H plus So those aqueous things. However, this is actually a reaction that goes forwards and backwards, and the backwards reaction is favored because only 1% of this is actually getting dissolved, is actually getting electrolyzed. It's actually breaking up into ions, ionized. That's the word I'm looking for. Most of it is sticking around as starting material, and that's what a weak electrolyte does. When you put a weak electrolyte in water, it dissolves, but it doesn't ionize much, and a little bit of it does. And weak bases, the equations look a little bit different. Again, they dissolve, but you'll actually produce OH ions in this case, something like ammonia. So we won't see a lot of weak bases, but we will see ammonia. You've probably heard of that one before. And it's the same kind of definition. Only about 1% of the ammonia molecules become ammonium. So only about 1% ionization in solution. And you can look at in your book, there's a table of acids and strengths and such. Right. Non-electrolytes? Well, I'll give you a hint. No, you give me the hint. We talked about several cases of molecules, substances, whatever you want to call it, earlier, a couple chapters ago, when we talked about naming. Right? Now we've mentioned a few of those classes, but we've left some out. So what types of things do not tend to electrolyte, ionize? What types of compounds tend not to be electrolytes? Can you generalize that in any way? Well, let's look at what do. And think about the categories of things in terms of naming. We talked about ionic compounds, and we said most of those become electrolytes. Right? Most of those are strong electrolytes. We talked about acids, and we said some of those are strong electrolytes, some of those are weak electrolytes. So what's the other class of stuff that we haven't really talked about? What? Yeah, covalent molecules of the nonmetals. Covalent molecules made up of nonmetals, so things like methanol, formaldehyde, nitrous oxide, various molecules that we've named over the time here. One important thing is they generally have to also have this polarity. So molecules made up of only carbon and hydrogen, it's true that they're non-electrolytes, but they also don't dissolve in water. Okay, so all of that was sort of a big build-up of some background information so that we can actually talk about concentration in solution. Generally, the reactions that you do in a chemical reaction are not in the solid state. Some of them are. Many of them maybe, depending on what branch of chemistry you're in. But most of them do not involve taking one powder and another powder and grinding them together and doing a chemical reaction. Most chemical reactions involve in solution. You take one thing, you dissolve it in a solvent. You take another thing, you dissolve it in a solvent. You put those things together, and you do a reaction inside a solvent. Then you get the solvent to go away somehow or something, and you have your product. So what that means is we need to have good ways to measure and talk about how much stuff we have when it is dissolved, when it's in solution. So far we've talked about how we measure stuff when it's just solid and separate. We weigh it, we convert to moles. Now we're going to talk about how we measure it and talk about it in solution. The amount of chemical present in the solution is often expressed as what we call a concentration. And there are various measurements of concentration. We're going to talk about a couple. The main one that we talk about in chemistry is called molarity. And here's its definition. Molarity is moles of solute, so moles of the stuff you're putting in, per volume of solution in liters. So moles per liter. Another way of expressing that, molarity, big M, moles of solute divided by 1 liter of solution. Now, the one important point here, we'll get into some of these calculations, but the denominator is liter of solution, not liter of solvent. So to make a solution of a proper concentration, you take your solute and you add enough solvent to bring it up to a 1 liter or whatever level. This does not mean that you take a certain amount of solute and a liter of water and mix those together. That would not be the correct concentration. So you're dealing with volume of the whole solution, liters of the whole solution. Let's calculate some molarities. So how would you calculate the molarity of a solution prepared by dissolving 11.5 grams of solid sodium hydroxide in enough water to make 1.5 liters of solution? What would you do first? Yeah, you got to convert grams to moles because this equation tells us moles of solute, or we need moles of solute to find molarity. So we're going to take 11.5 grams sodium hydroxide and convert it to moles. Is that 50? No. 40, right? And that gets us how many moles? Okay. Then what do we do? Right, so we take our 0.287 moles NaOH, divide by 1.50 liters of solution, and you end up with 19 what? So we would say that the concentration of this solution is 0.192 molar. And it's expressed with a big M. 0.192 molar. Okay, yeah. Yes. No, but no, the measure is per 1 liter, but you can make it however you want. It's kind of like you can say per liter. Like we have grams per 1 mole. This is moles per 1 liter. When you divide these out, essentially you have 0.192, which is 0.192 moles per 1 liter. That's what the measurement is after you do that division. All right, so you do this one. Calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous HCl in enough water to make 26.8 milliliters of solution. All right, let's try it. So we're going to do the same thing. 1.56 grams of HCl divided by 36.5 grams per mole is what? 0.4 what? We need one more here. We'll try to be good this time. 0? Oh, 0.0426. All right. And then what are we going to do to find the concentration? Divide by the volume of the solution. Okay, in liters, right? So that means we take 0.0426 moles HCl, and we divide that by 26.8 milliliters. So that's 0.0268 milliliters of solution. Whoops, that's liters, yep. And that comes out to 1.52 molar. Yeah, that's what I've written down too, actually. All right. 1.59 molar. So we would say that this solution is 1.59 molar in HCl. We can also say that there are 1.59 moles of HCl in every 1 liter of this solution. All right. So far, so good? Okay. A couple more examples, and then we will take a break and then come back to talk about dilution. Give the concentration of each type of ion in the following solutions. Now, we get a little bit trickier. We're not looking at the concentration. We're rarely looking at the concentration of the whole substance because it breaks up into ions in solution. Oh, that's not true. Sometimes we are. But it breaks up into ions in solution nonetheless. So if we have a solution that is 0.50 molar in copper nitrate, what is the concentration in copper? So what's the concentration of copper ions in the solution? What do you think? 0.5? Yeah. Well, let's look at what this means exactly. What? Oh, I thought you did. It sounded like it. Okay. Sure. Somebody else did. It sounded like it came from that side. Maybe not. So this means what we're effectively saying is that there are 0.5 moles of copper nitrate in each liter of solution. That's what the molarity is telling us, right? So we know that when we actually dissolve this in solution, I'm sorry, I've been saying copper. I can't see. It's cobalt. CO, cobalt, not copper. We know that when this actually dissolves in solution, this becomes cobalt 2+ and 2 nitrate ions. Right. So when this happens, we're basically doing a mole ratio as we did with theoretical yield before. We're saying for each mole of copper nitrate, we form 1 mole of copper ions, but we form 2 moles of nitrate ions in solution. So the answer to this question is that in this solution, our concentration is 0.50 molar in cobalt, but it's actually 1.00 molar in nitrate. So this molarity was expressed in terms of the compound before it dissolves, but in the actual solution, the concentration of nitrate is 1 molar, whereas the concentration of cobalt is 0.5 molar. Do you see why that is? Maybe? Yeah, because of the ratio. If you think about even though we know it's an ionic compound, think about the cobalt nitrate as a molecule that has 1 cobalt atom and 2 nitrates. So if you have one of those and you dissolve it in solution, you still have 1 cobalt ion now, but you have 2 nitrates because they broke off. That's what this is expressing. The molar concentration then is going to be dependent on the number of ions that go into solution. So let's do a full calculation now. Using the same idea, calculate the number of moles of chloride ions in 1.75 liters of a 1.0 times 10 to the minus 3 molar zinc chloride. What's your strategy here? What do you think you have to get first? What quantity do you have to try to find, do you think? Moles. You need moles first, right? And then we're going to get moles of zinc chloride first, and then moles of just chloride based on that. All right, so here's how we use molarity to find just moles. It's kind of a backwards calculation. We start at 1.0 times 10 to the minus 3 moles of zinc chloride per 1 liter of solution. That's what the molarity means. And then we're going to multiply that by the number of liters, or by the volume, in order to cancel. So we'll multiply that by 1.75 liters. Liters cancel, and we're left with just moles. We will. So that's how many moles of zinc chloride we have in that 1.75 liters of solution. So now how do we figure out the number of moles of chloride ions? Yeah. Are you sure that was your answer this time? I think I heard it coming from somewhere else. Okay, no. Yeah, you're right. You multiply this by 2 because there are 2 chloride ions for each zinc chloride. So in that 1.75 liters of solution, there are this many moles of chloride. That's going to become important because we can use that now in our stoichiometry calculations. When we want to find limiting reactants and theoretical yields, we can start from solutions, from concentrations, rather than masses, and do the same types of things. So we're going to do that. Let's take 15 and come back and give that a try.